Welcome back to the Tech Tutor. Now that we've covered asymptotic notation and how we classify algorithms, it's time to apply this knowledge practically. In this lesson, we'll analyze running times, explore algorithmic pitfalls, and measure empirical performance. If you're serious about writing efficient code, this is a must-watch. So, what factors affect running time? First, we have the input size, represented as n. The larger the data set, the longer the execution time. Then we have hardware performance. Your processor, memory speed, and storage influence execution times. Finally, the programming language and compiler optimizations can also make a significant difference. To understand how we measure algorithm performance, let's count operations. Consider a simple loop, summing the first n numbers. A single loop runs at O of n time. Now, if we introduce nested loops, the number of operations grows quadratically, leading to that O of n square. Okay, complexity. In contrast, logarithmic loops shrink the problem size each iteration, resulting in O of log n. One of the biggest pitfalls is inefficient sorting. Bubble sort takes O of n squared, while merge sort achieves O of n log n. Similarly, naive recursion, such as calculating Fibonacci numbers directly, leads to O of 2 to the power of n. Complexity. By optimizing with memoization or iterative approaches, we could reduce it to O of n though. But theoretical analysis isn't enough. We need empirical data. So profiling tools help measure actual execution times. Python's time module or C++'s chrono library lets us benchmark algorithms. This allows us to compare theory with real-world performance. Let's analyze sorting algorithms in action. Merge sort is O of n log n. Quicksort has an average case of O n log n, but a worst case of O of n square. Bubble sort remains inefficient at O of n square. Empirical tests, however, confirm theoretical predictions. Also, time complexity isn't the only concern. Space complexity matters too. Recursive calls, for example, could increase stack usage. An iterative solution may save memory compared to a recursive one. Always balance time and space constraints in your applications, even if it's simple as writing a program, right? So that wraps up our deep dive into practical algorithm analysis. Understanding complexity helps us write better code, and profiling tools validate our theoretical understanding. Make sure to like, share, and subscribe for more data structures and algorithms content. See you in the next video, guys.